Okay, so we are going to move on to section 4.2 today. And just so you guys are aware, I know I told 6th period this, but I think I forgot to tell 7th. You guys are going to have a quiz over section 4.1, whatever the next day is we have school, whether that's Monday, Tuesday, whenever. Okay, in class, you're going to have a quiz on section 4.1. Make sure you study very well for this. It is a pretty detailed quiz and a very long quiz. Okay, people get it and they're like, I thought this was a quiz, not a test, because it is stapled together. So make sure you are prepared for that because it is tricky. So today what we're going to be doing is we're going to be looking at the quantum model of the atom and the people who helped create it. We're going to look at, I believe it's 2 different people, what they created, and we'll also watch some videos as to help us visualize this a little bit. So Louis de Broglie said, if waves can act like matter, why can't matter act like waves? So Albert Einstein said that waves or light also can act like matter, right? You can have those massless particles called photons that act exactly like matter. Well, why shouldn't it be the other way around? And he actually created a formula for this. Hold on. Okay, that's what I thought. He actually created a formula for this, which combines those 2 equations that we learned earlier in this chapter. So it's like, oh gosh, I don't remember. It's like F equals, like wavelength equals HF divided by something. Let's just pull it up on Google really quick so I can show you what it's like. So it's known as the de Broglie equation. See, look at that de Broglie equation. So it is lambda equals h divided by mv. So you're going to take, what you actually do is you have lambda, and then you take Planck constant divided by the mass of whatever particle you're looking at and multiply it. This is by its velocity, but I'm pretty sure it's supposed to be by the frequency. You're really taking all of those equations and putting them together and just adding that mass portion in. And so there's an experiment done that was called the double slit experiment that actually looks at this and says, can matter act like a wave? Okay, so de Broglie thinks he has an equation done, and then there's going to be experimental evidence that may or may not back it up. So we're going to take a look at that really quickly before we move on. There it is. Here we go.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the 2 tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through 2 slits, we get this, 2 bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter, through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never-world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Okay, so de Broglie's question, if waves can act like matter, why can't matter act like waves? Well, it turns out, just like he figured you could figure out mathematically, it totally can become, matter can totally act like a wave, as shown in the double slit experiment. So when we're saying, like, when it said that a wave and the particles are in superposition with each other means that they are there together simultaneously. Okay, you can't have one without the other. They're there at the exact same time, always together, which is interesting. But so if you ever hear anything, two things are in superposition of each other, that's what it means. Even though if you type it into Google, superposition will come up with like the order of position or the order of like things occurring, which is interesting because in science we do use that term when we just talk about laws of superposition in rocks, in dating rocks. But when we're talking about two things in superposition with each other, we mean they're both there at the exact same time. Okay, de Broglie's equation was shown true through here, and when we're talking about the quantum world, remember, quantum is a little packet of energy, and so as soon as we came up with that idea of a little packet of energy, everything blossomed from there into, well, that little packet of energy created the dual theory of light, saying wave is a particle, and then now de Broglie has said a particle is also a wave. Okay, so quantum model of the atom, because that was our stepping point to get to this point. So everybody was like, okay, great. So how can something be both matter and energy at the same time? Those aren't even the same thing, right? Energy is just energy, and matter is when you have something that has mass and takes up space, even though apparently photons don't do that. Erwin Schrödinger is the one who created the best analogy and the best like mind thought process to explain this. And this is called Schrödinger's cat, which is something I brought up like last week. I said something, he's dead and alive, just like the cat, Schrödinger's cat. Okay, Schrödinger's cat is the butt of a lot of jokes, but it is the best analogy that has ever been created, and it is very widely known, and it's something you even need to know leaving high school to be literate and scientifically literate. So we're going to watch this video that explains Schrödinger's cat experiment.
This wouldn't be a YouTube channel without a cat video. So without further ado, we present Schrödinger's cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrödinger preferred poisonous gas. But whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we'll see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode, or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode and the cat doesn't see it explode. There's no option, the powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment, and it's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse? This collapsing to one reality problem is one of the biggest unanswered questions in quantum physics. So for Kitty's sake, can I has answer please?
Okay, so that video is very short and it goes through a lot at the same time. So I'm just going to rewind it and have you watch it again because I don't remember a year that we haven't watched it again. So it's really interesting because the first time you watch it, you're like, what? And then the second time, you're kind of like, I get it. So we're going to watch her again.
This wouldn't be a YouTube channel without a cat video. So without further ado, we present Schrödinger's cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrödinger preferred poisonous gas. But whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we'll see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode, or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode and the cat doesn't see it explode. There's no option, the powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment, and it's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse? This collapsing to one reality problem is one of the biggest unanswered questions in quantum physics. So for Kitty's sake, can I has answer please?
Okay, so Schrödinger's cat, both dead and alive at the same time. It's an analogy that's the most widely accepted analogy and thought process that explains how two things can be one, or how something can be two things at once. Okay, just like a particle and an energy. A particle can be energy simultaneously, and energy can be a particle simultaneously. Just like the cat was both dead and alive at the same time until we looked, right? And then when we looked at like the double split experiment, something else happened. So who knows, if you do it so many times, maybe the results will change. It hasn't so far. Whenever we look, it goes through the splits as a particle instead of as a wave. So Schrodinger's cat is a very important thought analogy. It gets brought up a lot in different circles. It gets brought up on Jeopardy. It gets brought up on like other quiz shows. Okay, it's something that you guys need to know. So quantum theory is what Schrodinger ultimately was also famous for inside of the scientific world, other than both having a cat that's both dead and alive, so no one knew if he really had a pet or not. Quantum theory describes mathematically that wave properties of electrons and other small particles. So what frequencies and when does it act like a wave versus a particle? So he was able to come up with some kind of some ground rules with math saying that electrons act like a waves when this is occurring, and other small particles do as well. So de Broglie's equation was what he used to actually come up with some of these patterns and things. So specifically what he looked at again was the frequencies of photons of light that it was emitting, and when would it act like a wave versus a particle when we're talking about those very small subatomic particles known as electrons. Okay. So Werner Heisenberg is the next guy. It's actually probably Werner Heisenberg because he's German. So if you didn't know, W's sound like V in German. He had another question, because that's what scientists do. They ask a question and then they figure out a way to solve it. Okay, so if electrons are also waves, where are they in the atom? So if you think about that, okay, so all of these pieces of matter are also waves, and especially electrons, as we saw in the double slit experiment. So where are these pieces of matter if they're also waves? Where'd they go? Okay, so he came up with this idea known as Heisenberg's uncertainty principle in 1927. He said it is impossible to know both the position and the velocity of an electron or any other particle. You cannot know both at the same time. This does technically hold true with macroscopic objects, so macroscopic objects, things that we can see with our naked eye, but it for sure holds true with microscopic objects, and especially subatomic objects such as electrons. And this is kind of a really hard thing to visualize, but we're going to do so whenever we come back to school using either a helium balloon, or if it's really icy and really cruddy out, which it probably will be, and I don't want to go to Dollar Tree, then we will just use a normal balloon, and that works as well. So whatever the next day is we come to school, we're going to do this demonstration activity thing that you guys will be actively involved in, and that will be your start, and you're welcome back to school. So this is where we're stopping now. You have no homework over the weekend, but then whatever day we come back, we're going to have a lot to do because we don't have any extra time built into our schedule right now. So what you're going to do is you're going to take your quiz, okay, over 4.1, and then we're going to do the balloon experiment, and that's what we for sure need to get done that next day. And okay.